Hello and welcome to Lecture 17. In this video we're going to be talking about the derivative of inverse functions as well as logarithmic differentiation. So I'm going to begin with a theorem that describes how to find the derivative of an inverse function. So here's the theorem. It says, suppose f of x is a differentiable function, and is 1-to-1. We'll say, so let's say g of x is equal to the inverse of f. If b is in the domain of g of x and f prime of g of b isn't equal to 0, then the derivative of g at b exists, and this is how you calculate it. So you can think of this as a derivative rule. So the derivative of the inverse function at b is equal to 1 over f prime of g of b. So this is why we require this condition right here, because we don't want this fraction to be over 0. So this is the general rule to find the derivative of an inverse function. You can think of it as just like the power rule or the chain rule. It's like a new rule for inverse functions. Let's show why this is true using a previous rule we already have. So recall that f of g of x in this situation described would be what? Well, f and g are inverses of each other, so they cancel and you just get x. So recall that that's true for inverse functions. That's all the way back to like lecture 1 through 4 material. So now let's take the derivative of both sides with respect to x. So if you differentiate the left side and the right side, this is what it looks like. How do you do the derivative of a composition of functions like this? You use the chain rule. So I'm just going to write what the chain rule is, because that's all this is. So the chain rule is you take the derivative of the outside, plug in g of x, and then you're going to multiply by the derivative of the inside. So this is just the chain rule that I did. And then the right side's a little easier. What's the derivative of just x? That's 1. And then finally, if I want g prime of x, the derivative of the inverse, I would solve by dividing both sides by f prime of g of x. And that's exactly what I have here for my rule. This is just for any x, and this is for a specific x value b. But this proves the rule for all x, where x is in the domain. OK, so all we had to do is use the chain rule to get that rule, which is pretty nice. Let's look at an example. So let's say f of x is x to the negative 3 power. So for all x values in its domain, this is going to have an inverse. And we're going to say g of x is equal to that inverse. And if you think about it for just a moment, what would I need to plug into this to make sure I get just x out? It would be x to the negative 1/3. So this is the inverse of this function. You can do the whole y equals this and switch x and y and then solve again. But this is what you're going to see the inverse is. So this is the inverse of this. Let's take the derivative of the inverse first. So the derivative of this function, use the power rule. You get negative 1/3 x. And if you subtract 1 using the power rule, you get negative 4/3. So this is the derivative of the inverse function. However, let's do it using the formula now. So this is one way to do it, if you can actually find the inverse first. Let's do this one. So we know g prime of x is equal to 1 over f prime of x of g of x. I don't have f prime of x yet, but I can find that. So right above here, this would be negative 3 x to the, and I subtract 1 and it's negative 4. So then I'm going to plug g of x into f prime of x. So I'm going to get 1 over negative 3. And here I'm going to plug in g of x. So my g of x is this, x to the negative 1/3. And that's going to be raised to the negative 4. OK, and in simplifying this, I get negative 1/3. Here I have a power to a power. So this is going to be x to the positive 4/3, because both of these are negative. And then this is equivalent to just saying negative 1/3 x. And if I move this to the numerator, I'd make the power negative. And notice, this is the exact same thing as I got by directly finding the inverse and then taking the derivative. OK, so I'm just showing you that both of those ways are equivalent. So that's nice that that works out like that. Let's look at an example where it's difficult for you to find the inverse in the first place. So we're going to let g of x be the inverse of f of x equal to x cubed plus 2x plus 4. And the question says find g prime of 4. So we'd like to find the derivative of the inverse at 4. The problem is, this is really hard to explicitly find the inverse for. If you set y equal to this, and you switched x and y and tried to solve for y, you'd have a very difficult time doing that. So in this case, it is very difficult to find g of x, the inverse, explicitly. So we can't really use the first method I used here before. What I can do, though, is use my formula over there. So we need to make some observations. First, I'm looking for g prime of 4, so I need to relate that to the original function. Notice that f of 0 would be 4. What does that mean for the inverse? So for the inverse, you flip all the x's and y's, so that means that g of 4 would be 0. So that's good to know. Let's use the formula now. So g prime of 4 is equal to, I'll follow this formula, so 1 over f prime of g of 4. And luckily, even though I do not have an explicit formula for the inverse, I do know what g is at 4, what the inverse would be at 4. It's 0, just based on knowing f of x. So this is 1 over f prime of g of 4 is 0. So this boils down to, do I know what f prime is at 0? And currently I don't, but I can quickly go over here and find what the derivative is. So the derivative of f is going to be 3x squared plus 2, using my power rule. So then that means f prime of 0, if I plug that in, it's, oh, not 0, it's 2. So here I'm going to plug in 2, and I'm going to get 1/2. So it turns out g prime of 4, or the derivative of the inverse function at 4, is 1/2. OK, from here I'm going to continue on, and I'm going to show you some more derivative rules. We're going to revisit the inverse trig functions and also the ln function. I'm going to use this formula to kind of help me find the derivative rules. So I'll see you in just a moment. OK, so now I'm going to use the idea of that derivative of an inverse function to help me look at this. So I'm going to look at the derivative of inverse tangent. We're going to prove what that is. So first thing I'm going to do is I'm going to let f of x be equal to tangent of x. And then I know what the inverse function is. We've talked about it before. We're going to say g of x is equal to f inverse of x, which is my inverse tangent function. OK, so we know that the derivative of the inverse function is equal to 1 over f prime of g of x. So we know that based on the rule we just learned. What I would like first is to find f prime of x. So let's put that right here. So based on our derivatives of trig functions earlier in this unit, the derivative of tangent, you should know this, is secant squared x. So I know what f prime is. I'm going to draw myself a triangle to kind of see the situation of what's going on. So here's a triangle. We're going to go ahead and say that tangent inverse of x, this is just an angle. I'm going to call it theta. And if you were to apply tangent to both sides, you get x equals tangent theta. So that's just applying the tangent function to both sides. So tangent of theta is x over 1. I'm going to choose this angle to be theta. And I know tangent is opposite over adjacent. So that means that opposite over adjacent, these are x and 1. And then if I use the Pythagorean theorem, this will be the square root of x squared plus 1. So that completes my triangle. Now, let's continue with what I've got going here. So let's say the derivative of g is 1 over. The derivative of f is secant squared. So I'm going to have secant squared of, and I'm going to plug g of x into the derivative of f. So g of x is my tangent inverse, but I'm actually just calling that theta right now. So I'll put theta here. And now let's figure out what secant is here. So we know that cosine is adjacent over hypotenuse. So that means secant theta is going to be hypotenuse over adjacent, right? So for secant squared, I'm going to need hypotenuse squared, which is this one. So it'll be hypotenuse squared over adjacent squared, which is just 1. And then if I keep change flip, this will become 1 over x squared plus 1. So this turns out to be the derivative of inverse tangent. So I can write that as my rule now. This is the derivative of inverse tangent. So what I think you should do is you should try the derivative of sine inverse of x and see if you match the lecture 16 answer. Because remember, I did this derivative in lecture 16, the previous lecture, and I got an answer for it. So see if you can use this idea with this derivative rule to match what you got earlier, match what we got earlier. And then in that video, I told you to try doing tangent inverse, and you should have got this. So now you can check your answer from before that you got this. So it all kind of is all linked together. Let's do another one. So recall the fact that the derivative of ln of x, we proved that that was 1 over x using implicit differentiation before. But let's now use this technique, which I think might be even more straightforward. So this time I'm going to say f of x is e to the x. The derivative of e to the x, you should know this one. This was back in lecture 11. This is just e to the x. Then what is the inverse function of e? We know that from our beginning material to be log of x. OK, so let's prove what the derivative of the inverse is going to be. So g prime of x is 1 over f prime of g of x. That's the rule, if f and g are inverse functions. This is 1 over f prime is e to the x. So I have e, but I'm going to plug g of x into where x is, and that's ln x. And e and ln cancel here, and I just get 1 over x. So very straightforward using the new rule that we just learned in this video. Let's do a couple of examples taking the derivative of stuff involving log. So first example is going to be the log of x squared plus x. Now remember, there's no rule that you can split this up, right? If there's multiplication in here, then you can split the log up as one log plus another. But there's no rule for this. So I'm going to use the chain rule. The standard formula is whatever's in here, you do 1 over that. That's the rule here. So we're going to do 1 over whatever is in here. That's the derivative of log. Times. Because this was a more complicated function than just x, we're going to use the chain rule and take the derivative of the inside. So the derivative of the inside is just 2x plus 1. So I can write that nicer by just saying it's 2x plus 1 over x squared plus x. So this required the chain rule, as well as the standard log rule, taking 1 over whatever's in there. And then I don't want you to forget about your log properties as you're doing this. That's why I mentioned this not being a log property. However, if we did the derivative of ln of the fourth root of x, this is equal to the derivative of ln of x to the 1/4. And then what can you do with a power here? You can bring it in front. That's a log property. So this is the derivative of 1/4 ln of x. If I have a constant sitting in front of a function, you can bring that to the front and ignore it when you're taking the derivative. So this is the derivative of ln of x times 1/4. And this is 1 over 4x, because the derivative of ln is just 1 over x. No chain rule needed for that one. So if you see powers and things like that, or multiplication, you could split logs, and you can make the derivative of this log much easier. These properties of logs do make very complicated expressions much easier to work with, and that's the idea that you're going to take into this next part of this video. We're going to use logs to try to make our differentiation easier. Okay, so I'll see you in just a second, and we can practice that. So now I'm going to show you the two types of situations that you want to be on the lookout for that would signal the use of logarithmic differentiation. So over here, we're going to do an example where you see an expression that's very complicated, that maybe has many radicals, exponents, factors, things that would be very difficult or laborious to use standard differentiation techniques for. So my first example is going to be y equals x cubed plus 2 times x squared plus 1 to the second power, all over the square root of x squared plus 5. So if you try to do the derivative normally, you would use the quotient rule overall. But while doing the quotient rule, you would encounter a chain rule, you would encounter a product rule, and another chain rule. So there's a lot of things going on here that could go wrong. So instead of having a giant expression as your derivative when you do a quotient rule, you can consider using this technique instead. So I'm going to rewrite this, because if you know me by now, every single time I see something with like a radical, I like to rewrite it as its rational power. So this is to the 1/2 power. So I haven't taken a derivative. I've just rewritten this the way I want it. And now what I'm going to do is, before you take a derivative, you take the log of both sides. So here I'm going to have log of y is equal to log of this entire expression here, x cubed plus 2, x squared plus 1 squared over x squared plus 5 to the 1/2 power. And what we're doing here is we're going to take advantage of all three of the log properties to make this something really nice and split it into just a sum of very bite-sized pieces. So remember, if you have the log of something divided by something, then this is the log of the numerator. So log x cubed plus 2, x squared plus 1 squared, minus the log of the denominator, which is log x squared plus 5 to the 1/2 power. So that's using a log property to break this up into a subtraction. However, I can continue. So these two things are multiplied together. So this is going to split into log of the first one, which is log x cubed plus 2, plus log of x squared plus 1 squared. So you can split up multiplication by using this log property. This is minus. Here I have a power, so you can bring that in front of the log. This is 1/2 log of x squared plus 5. I'm not done yet, though. If you'll allow me, I'm just going to take this 2 and bring it in front, because I don't want to sit here and write a new line. So I'm just going to bring that 2 right there. This is as far as I can expand, and actually using our derivative rule now. Remember, the derivative of log x is 1 over x. If we use this rule, this derivative isn't so bad. So remember, this is equal to log log y if you follow the equality all the way back. I'm going to use implicit differentiation to take the derivative of both sides. So let's do the derivative of this with respect to x. So this is going to be 1 over, derivative of log is I do 1 over whatever is in the log. And then I'm going to use the chain rule to take the derivative of the inside, which is 3x squared. Continuing, I ignore the 2, because it's a constant. I'll do 1 over x squared plus 1. And then the derivative of the inside is 2x. Minus. Here I'm going to ignore the 1/2. And then I'll do 1 over whatever's in here, so 1 over x squared plus 5. Derivative of the inside is 2x. Equals the log of the right side here. So log of y is 1 over whatever it is. Derivative of the inside. So recall from the last video, to take the derivative of y, you do derivative of y is 1 times y prime. What I'm looking for is I'm trying to find the derivative. So here, my goal is to find y prime. That's the goal of the problem. So all I need to do is solve this for y prime now. I'm going to multiply both sides by y. So it's going to be y times all of the left side. And these will cancel here. I'm going to simplify as I go across if I can see things. So here I'm going to have 3x squared over x cubed plus 2. Plus, here if I multiply these together, I get 4x over x squared plus 1. Minus, the 2's cancel here, and I get x over x squared plus 5. This equals y prime. And if you want to, and usually for problems, what's going to happen is you're going to replace the y with what was in the original problem. So this y right here was this originally. So I could fill this in, and I can say that y is x cubed plus 2, x squared plus 1 squared, over the square root of x squared plus 5. That's my y, and then the rest of the answer, you just rewrite it again. So it's all this stuff rewritten again. So I'm not changing any of this. I'm just copying this for completeness. OK, and this is the derivative. It's a pretty complicated derivative. It would look probably worse if you tried to do the quotient rule to begin with. So there's a problem like that. So that was the first case you'd want to use log differentiation if you see something that could benefit from log rules. Let's look at a different example right here. I'm going to try to fit them here. So another time you might use log differentiation is if you see a function that not only has an x as the base, but also an x as the power. So just recall for a second. Let's go over here so I can save some space. Recall the following derivatives. The derivative of x to the third is 3x squared. So that's the power rule. You have an x to some kind of numeric value. So this is the power rule. We also had this rule when you have a constant to a variable. So if I switch the situation, this one was 2 to the x ln 2. But what about a situation where you have the derivative of something like x to the ln x? This isn't one of those two rules because not only do I have an x here, but I have an x in my expression up here. So in this case, where you see x in both spots, you could use log differentiation. So what I'm going to do is I'm going to let y be equal to the function I'm trying to take the derivative of. So this is x ln x. It's called log differentiation because we have to take a log of both sides. So that's always how you start. So we're going to take the log of both sides. We'll get log of y equals log of x to the log x. So I took log of both sides. What you can do, and what's so useful with this property, is you can take the power and bring it in front of log. So this is log y equals log x log x. And that's just log x squared, right? I should point this out now that I remember. This is equal to this. However, this is not equal to this. Be very, very careful to not make that mistake. So squaring the entire log function is not the same as just squaring x. Okay, so be careful. But these two mean the same thing. Squaring the function is the same as this. So be careful with that. That was just a sidebar. Now I'm going to take the derivative of both sides because this is pretty manageable. So using implicit differentiation, derivative of the left side is 1 over y prime. That happens almost always because you saw it happened over here, right? Yeah, right here. We had that step. So you usually see that on one side. Here I need the chain rule. So my outside function is something squared. So I'm going to bring the 2 in front, leave the inside alone, and the derivative of the inside is 1 over x. So now solving, I get y prime equals, and you're going to multiply both sides by y. So I get 2 log x over x. And what is y? Y was this original function here, so I'll plug it back in, x ln of x. If you want, you could simplify this a little more by saying this is 2 ln of x. I have the same base. X is the base, and if you're dividing, you subtract the power. So this is x. So 2 ln of x, x to the ln of x minus 1. So that's just another way to write it. I think it went off screen just a little bit, so I'll put, that says ln of x minus 1. OK, let's do one more example just to make sure we've got this. And I'm going to do my best to fit this right here. And I'm also feeling a color change, so that's what I'm going to do. So I'm going to change colors here for the last example. Let's try this one. Let's do y equals cosine of x to the x power. So again, it's really nasty because not only does the base have an x in it, but the power does as well. So it's a situation just like this, where we don't really have a standard rule for it. But let's use log differentiation. So take the log of both sides. So log of y equals log of cosine of x to the x. I like to use lots of brackets just to keep track of what's going on. You can bring the x in front of the log. So this is log y equals x ln of cosine x. Once I got it looking like this, I'm going to take the derivative of both sides. So this one, as usual, is 1 over y prime. What rule would I need here? The overarching rule here is product rule. I have x times ln of cosine. So derivative of the first one using the product rule. So we're using product rule. This is going to be 1. Derivative of x is 1. I'm going to rewrite the second function. Plus, I'm going to rewrite the first function. And now I need the derivative of this one right here, which is 1 over whatever's in here, cosine, times, what's the derivative of the inside? It's going to be negative sine x. So is there a way to clean this up? Let's see. I have y prime. This is not doing very well, so let me switch markers. Let's try this one. So we have y prime over y equals ln of cosine x plus, I see a minus sign here actually, so we're going to make this minus. We're just going to bring that minus all the way over. Sine over cosine is tangent, so I get x tangent x. The last step, as usual, is to take this y and multiply it to both sides like that. So here the final answer is I get y prime is ln of cosine of x minus x tangent x. And then I go back to my original y. So this y was right here. And I'm going to plug it in. So I'm going to get cosine of x to the x. And this is my derivative. Again, it would be very hard to come by that answer without a technique like this, because this rule has nothing to do with the two previous ones we've learned. OK, I believe that about wraps it up for this video. Go ahead and take care of your quiz, and send me any questions as usual that you have. OK, until next time, see ya.